So we were discussing about the concept of finding an expression for the bulk modulus denoted by K by using the alpha and beta. Okay, this was the concept which we were trying to discuss, and we considered a diagram as shown here. There is a cube, and it is being applied several forces along each and every possible direction. So we can see that. So Ty is the force that is being applied right along the y-axis. At the same time, there is another force, tensile force, that is Tx, which is along the x-axis, and another one, that is Tz, along the z-axis. Also, you can see that we assume that the total volume of the cube to be equal to 1. Right. Now, the characteristics of these tensile forces or tensile stresses are as follows. So, if when you consider Tx alone, this is going to increase the length of your cube along this x-axis, but at the same time, Ty and Tz will compress the size of the cube along OX. So Tx will try to increase the length, and Ty Tz try to reduce the length. Okay. Similarly, when you consider Ty alone, it tries to increase the length along y-axis OY. Tx and Tz will try to decrease the length along the y-axis, that is OY. Similarly, right, Tz tries to increase the length along OZ, that is a z-axis. At the same time, Tx and Ty, they are going to try to decrease. Okay, so this is the basic idea. Now let's try to write the lengths along x, y and z. Therefore, the length OX is nothing but, initially this is 1. So y1, we assume that the total volume of the cube is equal to 1, right? Which means each and every side has to be 1. 1 along x-axis, 1 along y-axis and 1 along z-axis means total volume is 1 into 1 into 1, that's 1. So obvious that initial size is 1. Plus, let's try to write now the change along x-axis is controlled by the alpha into Tx. What is Tx? The tensile stress along the x-axis. This is trying to increase, whereas the y and z axis there is a compression, so I write minus beta times Ty minus beta times Tz. So Tx is controlled by alpha, right? Whichever is the side that you are considering to increase will be controlled by alpha, and the other side, that is a lateral strain, right, is going to be denoted by beta. Okay, so anyway, I'll write what is alpha and beta after I write all the three equations of OX, then OY and OZ. So OY is equal to 1 plus, you see, alpha times Ty minus beta times Tx minus beta times Tz. So when you consider along y-axis, we know that the Ty will the Ty tries to increase. That's why it is alpha times Ty minus beta times Tx minus beta times Tz. This is obviously trying to reduce the length along y-axis, and OZ is equal to 1 plus alpha times Tz minus this is beta times Tx minus beta times Ty. Okay, these are the three equations governing the increase and the decrease in the lengths of OX, OY and OZ axis because of the tensile stresses denoted by Tx, Ty and Tz. So here we used alpha and beta, so let's denote what are they. So alpha is the linear, it's called as a linear strain, and it is per unit stress, linear strain per this is unit, it's a stress. So for unit amount of stress, how much strain is produced, that's given by alpha, and beta denotes the it's the lateral. Okay, it's a lateral strain per, once again, this is unit stress. So for unit stress, how much is the value of the strain? That's what we are going to consider over here. Now, if you want to calculate the volume, right, then what's the equation for volume? I need to multiply OX into OY into OZ. So therefore, the final volume is equal to, I have to write, this is OX, right, into OY into the OZ. So let us substitute. That is, OX is, just now we have written, this is 1 plus, this is alpha times Tx minus this is beta times Ty minus this is beta times Tz. Multiply this with the OY, which is 1 plus alpha times Ty minus beta times Tx minus beta times Tz, and the last term into 1 plus alpha times Tz minus this is beta times Tx minus beta times Ty. Okay, so now let us try to multiply. So we multiply each and every term that is present over here, right? So that's going to generate something like this. So first I multiply the first two terms. 1 into 1 is 1, right? 1 into, so the every term will come as it is. 1 plus this is alpha times Ty minus beta times Tx minus beta times Tz. This is when you multiply with 1. Next, you multiply with alpha Tx with each term. So this is plus alpha times Tx. Next, alpha Tx into alpha Ty, both are positive. So alpha square Tx Ty. Then this is positive, next term is negative, so this is minus alpha beta into Tx square. Okay, that's the term. Then I have next term, that is alpha Tx into minus beta. So this is minus alpha into beta. This is Tx Tz. That's the second term getting multiplied to all the four terms in the second term. Then I'm going to start with the minus beta Ty into 1. Then minus beta Ty into plus alpha Ty. So this is minus alpha into beta into Ty square. Okay. Then this is minus of minus is plus. There is a beta into beta, beta square. There is Tx into Ty. Then minus beta Ty into minus beta Tz. So this is minus of minus is plus beta square Ty into Tz. Okay, that's the term. Then we go to the last term. So that is minus beta Tz into 1 is minus beta times Tz. So minus beta Tz into alpha is going to give me, this is minus alpha beta Ty Tz. Then same thing, this is minus of minus is plus beta square Tx Tz, and the last term minus of minus is plus, this is beta square into Tz square. This is the first multiplication. I need to multiply this with 1 minus alpha Tz minus beta Tx minus beta Ty later. Okay, now we will try to simplify, and we'll always will try to cancel the terms if possible. So let's check. There is alpha Ty, beta Ty, Ty Tz. Let's try to cancel the terms if possible. So minus alpha beta tx square, anyway it's not there, alpha ty, I don't think any of the terms will get cancelled here. Ty tz ty square beta square tx ty, no, none of the term will cancel. Minus beta tx tz alpha beta, no. Okay, we don't get any of the terms getting cancelled. So what we do, we will go ahead and we'll multiply this further. Okay, so that is, this is equal to, now 1 into 1 is 1. So every term should get multiplied with this, then only we will be able to simplify this. Okay, so every term is getting multiplied with 1, so this whole term will come in place. Okay, so this is 1 plus alpha ty minus beta tx minus beta tz plus alpha tx plus alpha square into tx ty minus alpha into beta into tx square. This is minus alpha beta tx tz minus beta into ty minus alpha beta into ty square plus beta square tx ty plus beta square ty tz plus, sorry, this is minus beta times tz minus alpha into beta into ty tz plus beta square tx tz plus beta square into tz square. This is the first term I get. Now I need to multiply everything with alpha into tz. So that means, let's write the term now. This is equal to, sorry, this means, now I am multiplying with the 1 into minus alpha tz. So this is minus alpha tz. Now there is a possibility of getting the terms cancelled. Okay, I just have to keep checking. If at all something comes, we will be cancelling there itself. Okay, so 1 into this, that is minus alpha into tz. Okay, then this is alpha into this, so minus, there is alpha into alpha, alpha square ty tz. Okay, then the next term is alpha ty, one with all of them. Next minus alpha tz into this, next minus alpha tz into the first term, that's going to generate, plus this is alpha into beta into tx into tz. So just check whether you have alpha beta into tx tz. Yes, minus alpha beta plus alpha beta, it will cancel. Okay, then the minus alpha tz into this, so I get plus alpha beta into tz square. So alpha beta tz square, let me just verify whether we have that term. Alpha beta tz square is not there. It might come later, alright, so we'll simplify. Next, this term into the third term is minus of plus is minus alpha square into tx tz. Alpha square tx tz, again it's not there, we'll move on. So next term is minus of alpha into alpha is alpha square, this is tx ty tz. Then minus of minus becomes plus, this is alpha square into alpha square beta into I think we have a tx square over there. So this is tx square into tz. Okay, then the same term which we multiply further is this. So this is equal to minus alpha tz into this term. So there is minus of minus, that is plus alpha square into beta. This is tx into tz square. Okay, then the next term is alpha minus alpha tz. So this is minus of alpha into beta is alpha beta times this is ty tz. Then the next term is alpha into this term. So this is minus of minus, so plus this is alpha square into beta times ty square into tz. Okay, and then the minus alpha beta is getting multiplied with this term. So this is minus alpha into this is beta cube. So tx ty square into tz. Then this into the last term. So that should be minus of alpha beta square ty into tz square. I think we have this term. Alpha beta square ty tz. Okay, let's move on. I think somewhere we have to get that alpha beta square ty tz square. Okay, let's multiply further, then we might get that term. Okay, this is alpha beta square ty tz square. Okay, then minus of minus is plus. This is alpha beta tz square. So we have, you can see the terms getting cancelled. One term should be minus of alpha beta tz square, another should be plus. Okay, then we'll write this is minus of minus is plus. This is alpha square beta ty tz square. Okay, we have alpha square beta ty. This is minus, this is, oh, my mistake, sorry. Alpha square beta, no, it's not cancelling, sorry, I'll just cancel this. Okay, next term is this is minus alpha into beta square into tz cube. Okay, like this we can keep continuing the multiplication, and finally we are going to generate a number after all the cancellation, right? You get this term as 1 plus alpha minus 2 beta into this is tx plus ty plus tz. So alpha minus 2 beta terms will come for each and every tx, ty, tz. All the other terms will get cancelled. Okay, now what we do, we assume that the tx equals to ty equals to tz, that is equal to t. This means it is alpha minus 2 times beta into 3t. So now we need to calculate, this is the final volume. Okay, so this implies I need to calculate the change in the volume. How do you calculate? How do you calculate the change in volume? It is, right, the final volume minus initial volume. That's the equation. Final volume minus initial volume, right? So final volume we just have calculated, that is 1 plus alpha minus 2 beta times 3t minus 1. So this plus 1 minus 1 cancels. So the change itself is denoted by alpha minus 2 beta into 3t is the change. So this means I can directly calculate the bulk modulus. Therefore, bulk modulus K is nothing but, right, I have to write the stress divided by strain. Strain is nothing but this is alpha minus 2 beta into 3t. So tt will get cancelled. Therefore, the equation for bulk modulus is nothing but this is 1 divided by 3 times alpha minus 2 beta is the required equation. So that's the equation for what is called as bulk modulus. Okay, then next concept is you are going to calculate the expression for, let's say this is Young's modulus. So as per the definition, we know that the y is given by longitudinal stress. I need to find that divided by the longitudinal strain, right? So in one direction, how much is the stress? So we know that that is given by T divided by the strain is nothing but alpha times T, alpha into Tx, alpha into Ty or whatever. So I know that this will cancel out. So the Young's modulus y is given by 1 by alpha. Okay, this is the required function. All right, so let's move further. We want to calculate the third term and its expression. So this is the next concept, that is we want to derive the expression for the rigidity modulus. We want to calculate this. For that reason, let us draw a diagram. That is like this. Let us consider this particular diagram. All right, so this is how we consider a cube, original cube, right? So consider a cube of dimension L, right? So one side is L. Now we are assuming that the bottom of this particular cube is fixed. Okay, so bottom is fixed. You can see that the bottom is dotted lines, which is fixed. Okay, and the top of, or the top face of the cube, we are trying to apply a tangential force that is denoted by the T. Okay, so I can see that it is a tangential force, which means it has to apply parallel to that particular surface. So if at all I was looking at the perpendicular, then this would have been the case, but now it is not that. The force has to be tangential. Okay, so let's write these points for our reference, right? So that is, first we consider a cube of sides L. So L is the side, right? And let's apply the tangential stress, capital T, right, along the top face, of the cube. Okay, now I know that the tube gets deformed now. So what happens to the cube? Slightly it will move. The top side, what we are going to see, it actually slightly moves to the right. So which means the I'll change the color. So A moves to A dash and the B moves to B dash. So your figure becomes slightly tilted like this. Okay, so that's what we need to consider when we are going to look at the shearing action that is taking place. All right, so we'll write another point here. So this implies, right, the cube gets deformed, right, deformed to the A dash, B dash, CD. CD is still the bottom, it is not changing, but we know that A and B will move to A dash, B dash respectively. Now we have actually marked two angles theta over there. So one here and one here. They are same, right? Both are equal. So we can try to find this length, this value theta now. So therefore the theta is equal to, right? So just see here, there is a mark L here. That is actually this distance. The distance BB dash or A dash is L, small letter L, and you can see that the capital L is this vertical distance. Okay, right, the height is L because that's what we assume. Consider a cube of sides L, so one side is L and the small movement is small L. So how do you measure this? B into BB dash divided by BC. So what is BB dash? That is small letter L, and BC, you can see that this is the height, which is the capital L. Okay, now in the next step, we are going to look at the tangential stress. Whenever you are looking at a tangential stress, right, equal to the tensile stress T along BD and compressive stress along AC. Okay, so whenever you talk about the tangential stress, it is going to pull the particular axis in one direction. In all the other directions, it is going to compress it. Okay, so we'll write that point here just to make it very clear, even if we forget. So this implies in the next point, the tangential stress, right, tangential stress equals to the tensile stress along which direction? Along BD. Tangential stress, I'll just write T here, capital T along BD. So you see the B and D, that direction it is going to increase, but AC distance is going to decrease, correct? Because of this deformation, the distance between A and C will decrease. That's why I continue now. And compressive along AC. So let's go back to the diagram and understand what is happening. So originally you see that BD was this distance, okay, but now you see that this BD is increased. That's why we said along BD it is tensile strength, tensile stress. It's going to increase the length. At the same time, you see AC was like this earlier, but now the AC is this one, A dash C, because A moved to A dash, so this is the length. And I can see that this length is a smaller length compared to the original AC, right? So that's why we are going to call that as compressive along AC and tensile stress along BD. Very straightforward. Okay, by just looking at the diagram, we understand this. Okay, now the BD diagonal is going to increase as I just discussed, right? Increase in the length of the diagonal is nothing but we are going to, right? Let's make a point now. So you can see that in the given diagram, we have a point denoted by M, which is here. Okay, M is here and the B dash is here. So this much is the increase in the length. So M B dash is the increase in the length of the diagonal. So therefore the diagonal BD increases by how much? M B dash. M B dash. You can see that M B dash is the added part to that. Right. Now let us assume that there is a alpha value, right, which is the linear stress per unit stress. The same thing we'll assume. So let alpha is, right, the linear strain. This is per unit stress. This is the first thing. And let's write the beta. And beta is equal to the lateral strain per unit stress. One was linear, other one is lateral. Lateral, this is strain per unit stress. Okay, now this means what is the total strain along the diagonal? Okay, so therefore the total strain, right, along BD is equal to, right, along this diagonal, that is T is the stress into alpha is the linear one. There is linear and lateral. That's why T into alpha plus beta. That is nothing but, right, I can actually denote this as the change which is MB dash divided by the original length, that is BD. It was BD earlier, now it is increased by this value. Okay, now let us try to substitute the values. How to calculate the MB dash? So MB dash is nothing but it is BB dash into cos of B into B dash into M. So you can see that that's actually going to be an equilateral triangle, right? And you have the 45 degrees coming up. So I can write this as BB dash into cos of the angle, right? What is that angle? B B dash M. So where is B B dash M? The B B dash M is present over here. You can see that angle, what I am talking here is this angle. Okay, this is what is the angle, not theta, sorry, theta is already denoted. I will call that as angle B B dash M. Okay, that's present over here, right? Since this is 90 degree and other two angles are this, we can approximate that to a 45 degrees. So this means we can equate this as this is B dash into cos 45 degrees. Cos 45 is nothing but 1 by root 2. So I can write this as B dash by root 2, but B dash is L. So this is L by root 2. Okay, now let us calculate. Therefore, the term T into alpha plus beta, which we had left earlier, this is equal to now that is mb dash, uh, which is nothing but we just now calculated that as L by root 2 whole divided by BD. What is BD? BD is L root 2, correct? So I'll just show you that now, the value of BD. So you can see here, this is L into root 2. Root 2L is the BD. So already we have written that. We are simply substituting here. So the L by root 2 will go to the root 2 into root 2 becomes 2. So this is equal to L divided by 2 times L. Okay, but L by L is what? Small L by capital L is theta. So this can also be written as theta by 2. Okay, so let's move further. Therefore, what you want? So on the left hand side, I have T into alpha plus beta is equal to theta by 2. Right? Therefore, what is the rigidity modulus? Rigidity modulus is n. N is equal to T by theta. So if you bring theta to this side and alpha to the other side, that becomes 1 divided by 2 times alpha plus beta. So this is the required rigidity modulus. So our intention was to derive an equation to get the rigidity modulus, and we did that now. All right, moving further, let's go to the next topic. So that is, we try to find out a specific relationship now. So that is the relationship between the Y, Young's modulus, N, rigidity modulus, and K, the bulk modulus. Okay, now let us try to write the equations of each of them. That is, let's try to denote a K. What is K? K is equal to, just now we have derived 1 divided by 3 times alpha minus 2 times 2 into beta. Okay, this is also equal to, the beta can be written, if you take alpha outside, let me write it in this way. This is 1 divided by 3 times alpha into, this is 1 minus 2 times beta by alpha. Okay, but the beta by alpha is nothing but the Poisson's ratio, which is sigma. So this is 3 alpha into 1 minus 2 times sigma. So why? Because sigma is equal to the beta by alpha. That's why I have made a substitution like this. But what is 1 by alpha? I can see a 1 by alpha here. See, there is a 1 by alpha. 1 by alpha is nothing but it's y, Young's modulus. So I can replace that as y divided by 3 times 1 minus 2 into sigma. So this is the equation and relationship between k and y. So you know k, you know sigma means you can calculate y, or you know y and sigma means you can calculate k. Okay, so now what I do, I perform y by 3k. So this implies the y divided by 3 times k is equal to 1 minus 2 into sigma. I cross multiply. Okay, let's hold on to this and let's call this as equation number 1. Also, we know that there is another equation for what is called as n, rigidity modulus. What is rigidity modulus? 1 divided by 2 times alpha plus beta. So this means 1 divided by, I'll take alpha outside, this is 1 plus beta by alpha, right? So this is equal to, now I can write 1 divided by 2 times alpha into 1 plus sigma. right? Once again the same reason, sigma is equal to beta by alpha. And I also can replace 1 by alpha by y. So this means 1 by alpha, I can see I am going to replace that as y divided by 2 times 1 plus sigma. Okay, so on the left hand side I still have n. This implies, right, I will try to write y by n. So y divided by n is equal to 2 plus 2 sigma. So this is what I call as equation number 2. Okay, so equation 1 is y by 3k and equation number 2 is y by n, right? I'll write the equation number 1 once again, that is y by 3k is equal to 1 minus 2 sigma. This was equation number 1. So add them together. So this is equation 1 plus equation 2 is going to give me y by n plus y by 3k is equal to, so you have 2 plus 1, correct? 2 plus 1 is 3 and 2 sigma minus 2 sigma will cancel. Okay, so this implies I can write 1 by n plus 1 by 3k is equal to 3 by y is the required equation which relates all the three coefficients. Okay, all the three coefficients can be equated like this. All right, then let's move to the next topic. This is called as the limitation on or limitation of alpha values. So we know that, right, the elastic moduli, whatever you take, whether it can be the y or it can be n or also it can be the k, anyone you take, this has to be positive, right? So all the elastic moduli are positive. So you can, if you check each equation, we have a term called 1 by 2 sigma. So this implies the 1 minus 2 sigma which you have in each of the term is always positive. Only when this is positive, I can get every term positive. Okay, so 1 by 2 sigma is positive in the sense the 2 sigma should be, right, less than 1. Correct? So sigma has to be having a value of 0.5. So should be positive. This implies the 2 sigma should be less than 1. So sigma should be less than 1 by 2 or sigma should be less than 0.5 is the condition. So that every coordinate what we are seeing there, right, every modulus what we are seeing over there is a that should be positive. All right, then let's go to the next concept. This concept is called as the torsion of a cylinder. All right, so we need to consider a diagram first. So let's try to write that diagram. Okay, this is the first diagram, and there is another diagram that we need. I'll write that as well over here. So let me paste that diagram over here for our reference. Okay, now let's start the discussion of what is called as torsion of a cylinder. Now let us consider a cylinder whose length is L and radius is R. Okay, so let's start. The L is the length of cylinder, R is the radius. We can see that in the diagram. Okay, let this cylinder is clamped, right, at the upper end. In the sense, I am not able to move the upper end of the cylinder. Okay, but uh, we are trying to apply a twisting force at the bottom of the cylinder. You can see here, I'll change the color. So this side is fixed. I'm not able to move. But here you can see that you are actually trying to twist your cylinder in one direction. Okay, so that's why the twisting, we call it as a twisting couple. So at two sides, because you hold the cylinder at 2 points, one here and one here, and you try to rotate. Correct. So that means it's you are applying the force at 2 points. So force that is equal and opposite is called as a couple. Already we have seen that maybe in any other force chapter. Correct. So let's try to write this point now. Let a twisting couple is applied at the bottom of the cylinder. We are applying a twisting force. So this results in theta. Okay, so let us say that the bottom of the cylinder twists by an angle theta. So theta is the angle of the twist. Okay, you can see two things now. The original point B, which was here, is moved to this new location so that there is an angle at the center which is called as theta. This is one point. At the same time, there is another angle that can be measured because of the movement of B dash. Originally B was here, this moved to B dash here. So at this point, right, now you can actually measure an angle phi. So two things can be measured. Two different angles can be measured as per this particular point. Okay, so cylinder is considered as coaxial hollow cylinders varying length from 0 to some point, right? As a result of this, now we directly write, right, what happens with the BB dash. Okay, so from the diagram, I'm writing this, right? I'll directly write. So B dash is equal to the value what I can measure here is a x value, right? X was my radius, x into theta. That's the movement of the point B to B dash. Okay, that's the first thing, x into this. That is also I can give it by using the length. So length, right, that's the height of the cylinder into the angle phi. So we can see that phi can be measured over here. Okay, right. So this implies I can say I can measure the angle phi, which is x into theta divided by L. So let's call this as equation number 1. Okay, now let us say that there is a tangential force that is being acting on the cylinders, right? So we'll write in this way. Let delta F is the tangential force, right? This means how do you calculate the tangential stress, right? So therefore the tangential stress. So what's the equation for stress? Stress is nothing but force by area. So force is denoted by delta F, and the area is nothing but, right, 2 pi into radius, that is x, into dx. All right, so this is the equation number 2. Then if you know the tangential stress, I can go for a rigidity modulus. Rigidity modulus. So from the basic equation I am writing this. This is the tangential stress divided by the shearing strain. So just now above in equation 2 you can see that there is a tangential stress. So left hand side is n, that is rigidity modulus, is equal to, let's write that, that is delta F divided by 2 pi x into dx, right? This is the numerator, whole divided by the shearing strain, that itself is phi. So this means, let's try to write the equation for delta F. Therefore, delta F is equal to, take the whole denominator to the other side. Okay, that is 2 pi into n, 2 pi n phi into dx. 2 pi n phi dx, yes. Okay, so let me call this by equation number 3 and this by equation number 4. So how do you calculate? Now using this force I can actually calculate the couple, right? Therefore, because there are the twisting happens because of what is called as two forces together called as couple, right? Therefore twisting couple, right? Twisting couple is delta C, which is nothing but, normally I can say this is the tangential force. All right, let me write the notation later. Okay, let me write the wordings first. So twisting couple is equal to the tangential force into the distance. See, the force into distance is a couple. Okay, NCE, yeah, distance. So did not give a notation. Delta C is equal to, right, n into phi 2 pi x, okay, 2 pi x dx. This is the first term, into x, distance is x. That's how that much far it is. So you can see the equation number 2 to get the value of phi, right? So I will substitute the value of phi from that equation. So this implies the delta C is equal to, so I can write this as 2 pi n into theta. N theta by L is the phi, okay, 2 pi uh, 2 pi n theta divided by L into x cube dx. This is the term I am going to get. Now how to get the couple? This implies the couple is denoted by C. I have to perform the integration. So I'll take out the constants 2 pi n theta whole divided by L and integrate from 0 to r, where capital R is the radius. This is x cube dx. So what happens to x cube? This is 2 pi n theta by L. X cube becomes x to the 4 by 4. So 2 cancels with this as 2. Substitution 0 to r. So x becomes r now. Therefore, the twisting couple C is given by pi into n pi n r to the 4 times theta whole divided by 2L is the required answer.